Good afternoon. So thank you for letting me come and speak to you today. The goal of the discussion is to talk to you about how GaN can have an impact on net zero. Paolo's just spoken to us about how he's working on silicon carbide. Hopefully, as a result of this discussion, his IPG6 will be using GaN. Quick talk, mention about the company. So Cambridge Gan Devices, shouldn't be a big surprise. We're from Cambridge, and we make GaN devices. GaN power switches. The 4 items listed there are our values, and I think they resonate with some of the discussions that were on earlier on today around sustainability, collaboration, innovation. So we all know that we need to aim for net zero. 30 to 40% of our emissions today come from power generation and conversion. So we need to not only generate electricity more efficiently, but also use it more efficiently. If we look at DC-DC converters and onboard chargers, you can see that today there's a lot of IGBTs, silicon MOSFETs, silicon carbide. But from these slides, you can see that there's a general trend that gallium nitride will start encroaching in this area. It's really about the right tool for the job. It's not saying that GaN's going to replace everything. It's finding the right technology to do the right job. This is a reasonably standard graph of efficiency against power density. What you can see here is that silicon just can't achieve the efficiencies that you can achieve with wide bandgap materials. And even silicon carbide, can achieve very good efficiencies, but not as efficient as gallium nitride. What happens then is that you can then increase the switching frequency, and the switching losses of gallium nitride are much lower, and therefore you can increase power density even more. Obviously, increasing power density means that we end up with a smaller product, and that's also achieved by having better efficiency, therefore less losses, less heat generation. So compared to silicon, we can more than triple the density that's achievable with silicon, and up to half the losses of silicon. So this is one view of it, and is the traditional view. But I was listening to a sustainability workshop a couple of weeks ago from ETH Zurich, who were talking about the global warming potential and the circular economy. And actually, if you superimpose that on here as well, you can see that through the life cycle of a product, the higher the power density you can achieve, the less global warming potential, because it's a smaller product, it's easier to manufacture, easier to dispose, uses less materials. That all sounds great, but as we've heard, silicon carbide is pretty much the incumbent material today. So what are the barriers for gallium nitride? Main barriers are that the design needs to be complex for traditional gallium nitride switches. There's also some questions about the reliability and robustness of gallium nitride. So CGD approached this by having what we call iScan. So iScan is, we use a lateral GaN process, and the front end of our chip has an integrated voltage regulator. The big issue with GaN is that when you switch the device, so you apply a voltage to the gate, that gate can only be about 5 to 7 volts. If you go above that, you can start impacting the reliability of the device. The other problem is that it has a very low threshold, so actually it can also accidentally turn on because of transients and noise. So you have to drive it negative to stop it turning on. With the iScan, we allow, you only need you can drive it up to 20 volts, and you don't need to take it negative, because we have a Miller clamp integrated that prevents any noise impact. That means that the external circuitry is much simpler, which obviously improves the power density, but also improves the cooling, allows you more area for cooling. The other issue that you can have is that because of this gate, you can get the robustness is impacted by the transients that can hit the gate. What you can see on the left here is our technology versus a standalone eGaN on the bottom line. So you can see that the transients of up to about 24, 25 volts will kill a traditional GaN device, whereas the iScan device can survive up to 90 volts, which is similar to silicon and silicon carbide. And the other two graphs show the immunity to noise thanks to the IGAN. So one of the other things that we're looking at is that we've looked at, obviously, OBCs and DC-DCs is sort of the entry point for GaN into automotive, and then we can start building some reputation and reliability. But obviously the holy grail is to try and drive this into traction inverters where there's more win. As we all know, traction inverters, cars, the load on the car is generally light load for about 60% of the time. And that's where GaN can actually make a lot of contribution versus the IGBTs and silicon carbides that are used today. So the charts on the right show for our next gen product that at light loads we can have half the losses of an IGBT system. And even at heavy loads we can have 25% lower losses. We also believe that as GaN uptake increases and technology improves, there's also cost advantages in using this type of technology, both in terms of manufacturing of the product itself, but also the whole system level cost. So in summary, GaNs are around today. So you go on Amazon and you buy yourself a USB brick. Chances are it's probably got a GaN device in it today. So it's already commoditized at a consumer level, but so we now need to start driving it into the higher power applications such as industrial and automotive, where we can really benefit from the efficiencies and power densities, and also the overall life cycle, the sustainability potential of this technology. The chart I showed earlier didn't talk about the manufacturing differences of SiC versus GaN. SiC is a high temperature process, so even at manufacturing level, I think it's about half the carbon footprint by using a GaN device compared to a SiC device. As you've seen, we offer a robust technology that hopefully overcomes some of the barriers to GaN for entry. But this is our view. I think it's been spoken about a lot today about collaboration, and we need to be collaborating with the likes of people in this room and wider to try and make sure that we're developing the right products, the right technologies for the market. So I'm relying on feedback from you guys to tell me what we're doing right, what we're doing wrong, and what we need to do to head together. Through these robust improvements, we can then enhance the reliability. As I say, GaN is already commoditized in consumer, so there's more and more reliability data coming in, millions of units deployed, so that we can start building that data, which is obviously the other concern when it comes to introducing products into automotive. And as I say, as we scale, the next generation technology that we're going to be working on, or we are working on, improves the cost base for this system, and therefore it's also competitive from a commercial sense as well as from an environmental sense. So that's everything I have for today. Thank you.